Alrighty, folks. So this is going to be our first problem session based on the problem request discussion board for week 1. So that means we're doing sections 2.1 and 2.2. Homework 1, actually, I'm not sure. We'll just stick with that, because that's where all the problems came from. In general, you can also ask questions about homeworks for these, but given that this is the first week of class, that wasn't something that came up this time. So from section 2.1, and so just so right off the bat, I don't have written out plans to do every question that was asked, but I got at least one from everybody. And I try to sort of comment on the ones that I'm not doing. I try to relate them to ones that I am doing. So for instance, we're going to start with problem 3 from section 2.1. There was another request for problem 6, but they behave in exactly the same way. There's just a different function. So I'm going to talk about sort of the relationship there to try to cover more of this stuff. So problem 3 says let b equal 5 root t. And it says to estimate the instantaneous rate of change of b with respect to t when t equals 20 degrees Celsius. Right? So, looking at this problem, breaking it down to its pieces, this means that we really should consider this to be b of t equals 5 root t, right? When you're talking about something with respect to another thing, that means the first thing is your function and the second thing is your variable. And this rate of change, right, and specifically, I don't know why I stopped there, this instantaneous rate of change means that we want the answer to the limit as x goes to 20, whoops, not x, sorry, t, remember, because that's where the variable goes. When t goes to 20, right, that's where that comes from, of, now I'm blanking on, yeah, there we go, b of, forgetting what the notation that the book actually uses. Maybe it doesn't use this notation. Yeah, apparently it doesn't. I'm getting it mixed up with what comes in later sections. But we do have in this section what instantaneous rate of change means. And that means first that we look at the average rate of change, right, which we do have the definition of. This is usually f of x minus f of x naught over x minus x naught, and estimating the instantaneous rate of change means letting x naught get closer and closer to x, right? So that's sort of the definition of it there. For our purposes, we don't have f of x naught or x's at all. We have b of t, so we're going to be looking at b of t minus b of t naught all over t minus t naught. And one of these is always going to be, the t is always going to be 20, right, coming from this thing here. And t naught is going to get closer and closer. Right, so I said I would relate this to 6, and 6 wants you to do the same thing. It just actually gave you all the directions for it instead of expecting you to remember what the directions are. Right, so 6 says compute the stone's average velocity over time intervals, and it gives you some there. Right, and that's exactly what we're doing here. We're going to compute the average velocity, and we just get to pick the intervals instead of having them handed to us. But I'm going to use the same pattern that problem 6 does, so that you can use this maybe to help you out with problems like number 6. Right, so we're going to check for 20 to 20.01. We're going to check for 20.001, right? Because 20.01 is really close to 20, but 20.001 is even closer to 20, right? And then we're going to go even closer to 20. And because I worked this problem out ahead of time, I know that it'll be beneficial to go even closer to 20. Right? There's no rule for how close you need to get. It's really a matter of keep getting closer and closer until you can find a pattern. Right? So I'm going to plug in, I'm going to get b of t is b of 20 minus b of t naught is plugging in the other number all over 20 minus 20.01. I plug that into my calculator and I get 0.5589. All right, so there's no fancy tricks there, just plug it into your calculator. All right, same thing here. We use that exact same formula. We just have a different thing to plug in for the t naught. And that winds up getting 0.55901. Right, we do the same formula. And it's often kind of nice if your calculator has any sort of memory, right? Because the way I did this when I was finding these numbers is I plugged this first one in, and then I just went back and edited it to add a couple of zeros, or 1 0 at a time, rather, each time I went through it. And so I didn't have to type the whole thing in again. But then I did the last one, plugged it in, and I got 0.55902. And since I've been getting closer each time, and at least as far as my rounding is concerned, right, because this should technically be squiggly equal signs, because there's definitely some rounding going on. But at least as far as the amount of digits I rounded to is concerned, it started being exactly the same, right? It's not even getting close to something. It stopped somewhere. So my estimate is going to be this guy because these match. Right, we did a problem like this in the mini lecture, right, where it didn't match, but it was looking like it was going towards somewhere. So that's another thing that you have to be aware of. But for this problem, even getting 5 whole digits when we round, we managed to get something that was exactly the same. So that finishes us off there. Alrighty. So, and like I said, 6 was like this. You're going to use the exact same formula here. You're going to pick different numbers here, and in fact, the problem gives you which ones they want you to do. You're just going to have a different function to plug in and different values here, but you're going to do the same process for number 6 as well. All right, so the next one I wanted to do was number 10. So this says, I'm not going to write out the whole thing because we have our books, but I'm going to write out the important part, is that the atmospheric temperature is given by T equals 15 minus 0.0065 H for H less than 12,000 meters. It wants the average rate of change of T with respect to H. It wants the instantaneous rate of change of T with respect to H. And it kind of gives a clue as to what the answer is going to be, because the third question is, why are they the same? And the fourth thing is to sketch the graph. Right, and I'm actually going to skip straight to the graph because that helps answer the why, which, and it can kind of help explain where we get the first two answers too. Right, so this is a linear function, right? If this is T of H, that's what this T with respect to H means, is that it's a function like that. Right, and with a linear function, it's in slope-intercept form. So I automatically know that the intercept is at 15. Right, and the other thing that might come in handy is the end point. Right, so I know that this graph is only going to go out to 12,000. Right, and anytime you want to draw a line, you just need 2 points. So I'm going to figure out what T of 12,000 should be. Right, that's going to be 5 minus 0.0065 times 12,000, which I plugged into a calculator, and I need to find it on my sheet. That's apparently negative 63. So it's down here somewhere. This is clearly not to scale, but that's not really all that important. Right, it's going to stop there because this function doesn't let, right, this is the H, right, because that's the variable and that's the function, so that's H and T. And if it's for everything less than 12,000, it's forever down that way, but it stops here. Right, so that's our graph. That's a basic sketch of the graph. And if we think about what average rate of change is, right, let me grab some colors here. Average rate of change wants us to pick 2 points on the graph and draw the secant line between them. Right? But if we pick 2 points on a straight line and draw the line that connects them, that's exactly the line again. Right? So this average rate of change is supposed to be the slope. That's really not particularly readable, is it? Maybe this one will be easier. Yeah. Slope of the secant line. Didn't really leave myself enough room. We'll make it work. Right? But as we can see from this picture down here, the slope of the secant line is just the original slope. Right? Because the secant line and the function line are the same thing. Right? Similarly, for the instantaneous rate of change, that's the slope of the tangent. Right? And the slope of the tangent, the way you can think about the tangent is you pick 1 point on the line, just one, and then you draw a straight line that is as close to the function as it can get at that point. And it turns out that a straight function that is as close to the straight line that goes through a point as it can get is just the line through that point again, right? So that's going to be negative 0.0065. So what I would say is the answer to why are they the same is because t is linear, right? That's another one, one of the rules that we learned in this section is that linear functions have an average rate of change between any 2 points that's the same as the instantaneous rate of change at any point, at any 1 point, right? Because instantaneous rates have 1 point. So the average rate of change at any 2 points is the same as the instantaneous rate of change at any 1 point, which is the same as the slope of the function, right? And on one hand, that's a kind of a rule that we have now. On the other hand, it's because the secant line, the tangent line, and the function line are all the same thing by definition when you have a linear function. Right? So that was problem 10 there. Next up is another problem like number 3, but I wanted to do it purely to emphasize that the things that I chose there, the way that I chose to do that didn't depend on, for instance, 20 being quite such a nice number, right? This problem wants us to estimate the instantaneous rate of change of f of x equals e to the x at x equals e. Right, so again, this is going to involve looking at f of x minus f of x naught all over x minus x naught, where x is equal to e and x naught is closer and closer to e. So we start off with e, and before, remember I guess I don't have to just say it out loud, right? We did 20, and this is really 20 plus 0.001, right? It's 0.001 or 0.01 more than 20. We can do the exact same thing here, even if it doesn't look quite as nice. Right? And we get f of x is e to the e. F of x naught is e to the e plus 0.01. And then we have x minus x naught. Right. So I plugged that, again, I just plugged that into my calculator, right as it stands, and I got 15.2302. Right, we do the same thing, except instead of adding to whatever we started with 0.01, we're going to add 0.001, because that's adding something even smaller, and thus we're getting even closer to e. Right, and so we have f of x minus f of x naught all over x minus x naught. And that's going to equal and right, there we go. Then we can keep going a little bit further because it doesn't really look like it's settled down at all yet. So we get f of x f of x naught, x minus x naught, and we get that. And then looks like we're zeroing in a little bit, but if we go, I know that if we go one more, right, and we do f of x minus f of x naught all over x minus x naught, we get 15.154. And here, one of the things that I notice is that we don't match up all the way, but if we restrict ourselves to 2 digits, and maybe that's enough, right? Generally, the problem will tell us what we want to round to. In this case, it didn't, so we'll stick with 2. But since it matches up on those, I would be pretty comfortable with saying that 15.15 is our estimate, right? Because we matched up with at least that many digits for 2 of these instances of getting closer and closer, right? So the process that we used for number 3 here, right, where we took the value that it gave to us at the start, right, and we add 0.1 to it, 0.0 or 0.01, 0.001, 3 zeros, 4 zeros. We can do that even when the number is not as nice as 20. So even if we have to write it like this. So that's it for questions asked from section 2.1. So for section 2.2, we are almost certainly going to have to create a new thing for this, but maybe not, because we're going to be doing a lot of graphical stuff in section 2.2. But we're going to start off with problem 6. I just realized that there's 2 different ways. Okay, problem 6. Right. So that one gave us a picture. All right, so let me see if I can draw this accurately. We got here. We got here. We got here. This matches up. This matches up, and then it goes wee, and it keeps going. Right, and so the question was determine the limit as x goes to 0.5. This was supposed to be y equals g of x. Of g of x, as in this picture, right? So what we want to do for that, right, is first, if we're doing this graphically, first we want to find the limit as it approaches from the right. Then we want to find the limit as it approaches from the left. And then we want to see if those two things are equal, right? So if I want to find it from the right, right, if I want to find this guy, then I'm going to put my pen on the graph somewhere bigger than x equals 0.5, right? This is x equals 0.5, so I'm going to go somewhere bigger, but be on the graph, and then I'm going to draw a line along the graph until I get to that 0.5, except I'm not going to go till I get to that 0.5. I'm going to go up to, but not including that 0.5, right? And this requires remembering from our pre-calculus class, or maybe even before that, what a hole in that function means, right? Putting the circle there putting this circle here means that every number except the single one that it's over is on that line, and you're only missing at x equals 0.5, right? So for every number bigger than x equals 0.5, we're included on this line. The only thing missing from this line is exactly at 0.5, and this limit does not care about what happens exactly at 0.5. This one in particular cares only about what happens when x is bigger than 0.5. Right? And then for the other one, we choose any number over here to the left of 0.5. We put it on our graph. We draw the line, and again, we go all the way up to 0.05 without actually reaching it, and we get 1.5. And since those guys are equal, that's what the limit itself is, right? So the key thing for this problem, the key reason it has you working it, is to emphasize the fact that limits do not care what happens when x is equal to a, right? Limits care what happens around x equals a, right? So it cares what happens nearby that, not what happens exactly at 0.5, right? So since we can trace those lines on the function to get to 1.5, as long as we don't actually go to 0.5, because if we go to 0.5, we get 1 out of the function, right? But we're not actually going to 0.5 because the limit doesn't care what happens at 0.5, it just wants you to be near it. Right? So, next problem here is problem, or not 3.1, 31, right? And that one says estimate the limit numerically or say it doesn't exist if infinite, say which one-sided limits are plus or minus infinity. Right? Because remember, the definition of an infinite limit is that at least one and maybe both of the one-sided limits go off to plus or minus infinity. Right? So in this case, it's just saying make sure you can accurately describe them. So let's see. So this one's going to look a lot like the problems we were doing last section, except instead of having the difference quotient, we're just dealing with the function itself. So number 31 is the limit as h goes to 0 of sine h cosine of 1 over h. Right, so what we want to do here is, in this case, we're just plugging in the things close to 0. Right, in the problems we did last section, we were plugging in the point we cared about, like 20 or e, and things that were close to, because we had a more complicated formula. Here, we're just plugging in numbers close to the one we care about. Right, so first, I'm going to see what happens when h equals 0.1. Right? So that that's a number that's pretty close to 0. It's not super close, but it's pretty close. Right? And it turns out when I plug that in, I threw that into a calculator, and I got negative 0.0837. Now I want to get even closer with my next step, but I'm going to plug it into the function just like before. And I throw that into my calculator, and I get 0.00866. There we go. And I'm going to get even closer. Right, and I wind up getting 0.00562. Now I could keep going, and maybe should, but this seems pretty clear that we're closing in on 0. Right, let's see. I think I did do one more. I did h equals 0.0002. Because it doesn't necessarily have to follow some pattern as long as it gets closer to 0. And I got 0.00003. And then I can't read my handwriting, but that's more than 4 digits anyway. Right, so I'm pretty sure this is getting on towards 0. Right? This really looks like we're going to 0. But one of the things that I need to be careful about is that all of these numbers that I've chosen, they're all bigger than 0, right? So what I've really done here is estimated that the limit as h goes to 0 from the positive side of sine h cosine of 1 over h equals 0, right? And so I really want to make sure that it happens from both sides, right? But thankfully, I don't even need a computer or a calculator for the rest of this, because I know some nice things about the trig function. So if I'm plugging in a negative version of what I plugged in up here, that's into sine, that's going to turn it negative. If I plug in negative version of the same thing that I plugged up here into cosine, that's going to go away, right? If you remember, sine is an odd function and cosine is an even function. Might have been something that you talked about in pre-calculus class or trig class. And that means that I know, even without plugging that into my calculator, that this is going to be a positive version of what we had before. Right. And same for all these. I'm going to get negative 0.0086, negative 0.00562, and negative 0.00003 just by plugging in negative versions of h, because sine and cosine are such nice nice functions. Yeah. So I know that we're going to 0 on this side too. Right, so that means the limit as h goes to 0 from the left of sine h cosine 1 over h equals 0. So there we go. So putting these together, that means the limit as h goes to 0 of sine of h cosine of 1 over h is equal to 0. Right? Because all that needs is for the one-sided limits to both be the same. Okay, so I've run out of canvas here. Y'all are going to get to hear on the video, see behind the screen, behind the scenes, how this stuff gets made. I'm going to make a copy of this, and then I'm going to clear it. And we're going to start new. Okay, so for our second one, All right, we're still on section 2.2. Alrighty, so number 37. This one's gonna work, or this one's in the same section as the one we did last time, the sine of h, cosine of 1 over h. So it has the same instructions, but it looks like the limit we're looking for is the limit as x approaches 1 from the left of tangent inverse of x over cosine inverse of x. And so we could do this exactly like we did the last problem, right? Where we'd have to change it up. We're not plugging things close to 0 anymore. We're plugging things close to 1. So instead of plugging in 0.1, we'd be doing like 0.9, and then we plug in 0.99, and then we plug in 0.999, maybe 0.9999. So we'd be plugging in numbers that get really close to 1, but are always going to be less than, right? So the differences from what we do last time is we're getting close to 1, not close to 0, and we only have to worry about coming up from the left, right? We broke the problem up last time into a left and a right, things smaller than and bigger than, and in this problem it's specifically only asking about one of those. But that sounds like tedious and no fun. I have to have my calculator for this anyway, so I would rather go ahead and do some work with a calculator in general on its own, and have it do all the work for me. So the way we would do that is we would go to our calculator. Whoops, I left it on the wrong thing. We'd go to y equals here, right? This one on the far left that lets us plug in our function. So it's tangent inverse of x divided by cosine of x, right? That's the function that we're taking the limit of. And then I I still have this one set up from when I was practicing with it. So it's all set up in the right place, right? With 1 here at our starting point, right? It's even highlighted for us. Now, we don't know what happens exactly at 1, right? But like I was saying for the first problem in this section, we don't care what happens exactly at 1. We care what happens, in this case, very close to but less than 1, right? So we see that we can't get bigger than 1, certainly. That's not allowed, which is probably why this limit is only worried about things less than 1, right? But 0.9 isn't really close to 1, so maybe we want to change that up. And we do that by going to table set, right? If we click the window button here, we don't actually want this one. But table set we get by hitting second and then window, right? And then to get closer, we just make this number smaller, right? So maybe we make it 0, 1, right? Then we go back to the table. Whoops, I want to go to the table, I said. And here, it looks like we've started getting big. Yeah, right? We went from being like 1 and some stuff to being 5 and some stuff. So it looks like we're getting big, but we don't have any indication of what we're getting close to yet, right? So let's maybe go back to that table set. And you know what? Let's just put a whole bunch of zeros there, right? Just a whole bunch of them. We don't have to plug it in. We don't have to check this ourselves. We don't have to type those 20 times. We can just put it in here and it'll calculate for us. And whoops, I centered it at a bad place. So let's get back to x equals 1. All the way. All the way. All the way. I need to be careful about where I click before I do these things. Let's see if, yeah, here's what I want to do. Let's put that back to 1. There we go. Okay. So now with doing that, we've gone from 5 to 555. So we've gotten really big. Let's go to there again. Make sure we've highlighted that 1, so we'll stick there. Let's do point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see if it'll handle that. Let's see how it does. Oh boy, we're getting even bigger, right? It doesn't know how to handle it on the X. It just thinks, oh, it's close enough to 1. I'll just call it 1. But we know it's slightly less than 1, right? And we've gotten really big there. So what it really looks like is that instead of settling down somewhere, instead of doing any sort of pattern, it's just getting really big, right? And if we recall from our definitions, the fact that that gets really big means that this limit is going to infinity, right? Let's see, what other ones do we have here? Number 41 is also, so this one is determine the one-sided limits numerically or graphically. And if infinite, decide whether it's negative or positive. But this is our basic instructions. And 41 wants us to find the limit as x goes to 0 from the right of sine x over the absolute value of x. And it also wants us to find the limit as x goes to 0 from the left of sine x over the absolute value of x. So this is another one that I suggest going to a calculator for. Again, you could do it like that very first problem we did with sine x cosine of 1 over x. You could plug in some things really, really close to 0, fill out a table yourself, or you can just have the calculator fill out the whole table for you. So let's go to calculator. Again, we want to go to y. We want to reset this and have it be sine of x. Oops. There we go. Divided by. Now here's one of the tricky things. We need the absolute value of x, and that's not on any of the buttons that we have here. But if we go to math, that's what I clicked just there, and then we go over to number, we have that absolute value there. Whoops, except I don't want it here. I want to go math, number, absolute value of x there. All right, so if we wanted to do it graphically, we would hit the graph button here. Right, and then maybe we zoom in on 0. Ooh. So, right, and we could even say, hey, I want to look at what happens when x equals 0. Ooh. And it does weird things. So x equals 0. It's not doing what I wanted. But, you know, on a regular calculator, you can do zoom in using the zoom button. We want to figure out what happens when x equals 0. It's being weird, displaying behavior. Aha, that's what I wanted to do. So one of the problems with a calculator system, right, this calculator doesn't really know what to do inside these pieces here, right, at least graphically. So this one seems like one where graphically is not the best way to do it because we don't have a good way to draw this graph. Right, but maybe our table is good. Let's go ahead and set our table up. We're wondering about x being 0, so we want that to be 0. We might as well leave this really, really small. We could do some things adding up to it, but let's try it out and see how it behaves. So again, it's really confused. That's a number that's very close to 0, but not quite 0, which is why it actually has something, right? But this is something bigger than 0. this is something that is a little bit less than 0, and this is something that is infinitesimally bigger than 0. And here, we've actually made things small enough that we can tell right away. It's clear that on the left, right, on the left we get -1 for a long time, right? On the right, we get +1 for a long time, right? So we don't even have to worry about rounding and stuff doing it this way, right? Before, we had to plug in a whole bunch of things and sort of guess. The table that the calculator does is actually a very nifty tool. So according to numerically for this one, and I guess that is sort of what our graph was showing, right, when we do here, is that as close as it would let me get to 0, we were up here at 1, and then as soon as I crossed the line where x is now negative, it popped me down to -1, right? So we could sort of have told that graphically. It's just a little hard to tell when the graph is bugging out because numbers are too small and when it's actually telling those limits. So we could get it graphically as well. Right. Okay, so let's see. Next one was number 43. This is in that same block, so it has the same instructions. But it is asking the limit as x goes to 0 from the right of x minus sine of the absolute value of x all over x cubed. And it also wants to know the limit as x goes to 0 from the left of the same function. And I really can't encourage enough that we should go to a calculator for this, right? If you don't have something like a TI 80, whatever they're on now, like if you have a smartphone or a tablet, that's what I'm doing here. That was a free version of a TI app is what I keep switching over to. There's also applications for the computer, and there's also internet applications, right? If you look for a graphing calculator, you might be able to find some options for graphing things and maybe even looking at a table for those. So let's go back here and we want to clear this out. And we want to plug in that function. So we have x minus sine. And we want to get that absolute value again. So we have to go to math number absolute value of x. That closes out. There we go. One of those is to close off the sign, and one is to close off the top of the fraction. And we want to divide by x to the cube. All right. So now we can go look at the graph. Ooh. All right. And looking at this graph, right, it seems pretty clear, right, this is as zoomed out as it's going to let me be. But if I'm anywhere over here negative, right, especially if I glance at what the y value is doing here as I sort of wiggle my pointer on the negative side, that really looks like it's going to infinity over there on the left, right? It's getting bigger and bigger and bigger and bigger. But then as soon as I turn positive, it looks like it's going to about 0.1667, which I believe is 1/6. But we could also confirm that by doing second table, looking at 0, right? And here we have some really, really big numbers, right? Remember the E notation there is how many zeros you need to put after it, right? If it's a positive number, so what this means is 2 followed by 22 zeros, which is a very big number, right? Remember, this one is decimal point followed by 10 zeros followed by a 1, right? Because we're moving the decimal point 11 places to the left. So this is a very, very small number, and we get 0 here even, right? So it looked like it was going to 1/6, but apparently it's going to 0. That seems strange. Let's not have it be quite so ridiculous. Yeah, there we go. Okay. It was kind of two small numbers. It was thinking it was actually at 1. Which in this case does have a value, right? That this can figure out. It's just, it's got some rounding errors in there, right? So if we let ourselves get a little bit bigger, then we can see that we're at about 0.16 for a long ways there. And we are at really, really, really big numbers here to the left. So that means that to the right, we're going to 0.1667, it really looked like. And to the left, we're going up to positive infinity. Right. Let's see. We'll do one more, because it was one from another block. And the only difference in this block is it was specifically saying that you should do it graphically, right? So the first one, one we did here, specifically wanted us to do it numerically, right? So that's one where you find the table, and you show some values to show your work. These two said we could do it numerically or graphically, and so what I would do in either situation is, if I were trying to estimate it, do both and make sure they said the same thing. Right, but if you were doing this problem on, say, an assignment, and you didn't really want to go through the trouble of doing both, these two you could do either. This one, it really wanted you to use the table, and this one here, it's specifically saying to do graphically. So this is the limit as theta goes to 0 of sine of 5 theta over sine of 2 theta. Right. So if we want to go back to our calculator, we want to go to y, we want to clear all this out, sine of 5. Now, one of the things about the graph on a calculator is it's really geared up to work with x, right? So if you want it to graph a function, you need to take whatever variable you're dealing with and replace it with x. So instead of 5 theta, we're going to have 5x, and instead of 2 theta, we're going to have 2x. So this problem specifically wanted us to look at the graph. So that's exciting. That's a fun looking graph. And it wants to know what happens as approaches 0, as theta, or in this case x, approaches 0. So we can, my pen is on the blue ball here. So as I follow my graph up, it looks like it's getting closer and closer and closer to 2.5, right? And if I start over here on the left and I go up, it's getting closer and closer and closer to 2.5. Right, so it seems pretty clear. Right, it doesn't actually ever get up there. Right, I don't think it'll ever. Calculator graphs usually don't have that whole notation that we talked about at the very beginning, but we can see that it never actually reaches that 2.5 because it has to directly skip over 0. Because we can't plug 0 into this. But it gets really close to 2.5 on both sides of this. So just by looking at that graph, I know that that's 2.5. Right. Let's go ahead and do one more of those. It's not a big deal. Let's do number 62. Right, so that's limit as theta goes to 0 of sine squared 2 theta minus theta sine of 4 theta all over theta to the fourth. So we need to plug that into our calculator, which is going to be exciting. So sine of, what did it say? 2 theta, which again, we're going to turn the thetas to x's. And then we want to square that. It's a little, the calculator requires a little different notation than we usually use, but that's just the limitations of calculators. Whoops. Don't want to, no bad. There we go. Now, I want to make sure to get out of the exponent up there, so I can do my x times sine of 4x and close that off. Now I want to put parentheses around this whole thing to make sure it understands it's all on the top of the fraction, and then we have x to the fourth in the denominator. So if we look at the graph here, okay, so that was a little bit less exciting graph, but you know, we can still, to get the right hand side, we follow this guy up. Looks like we're definitely getting up. Let's see, we're on the left here. So I'm going to keep going as long as, whoops, stays negative. So it looks like 5.333, let's say. Right, I'm looking at the very little numbers on the screen, so hopefully they'll be easy enough to see when you're looking at the video. Looks like it's getting to at least 5.33. Right, 5.333. Then we go slight bit positive, and we're at 5.333 again. Right, so it really looks like we're getting up to 5.33 at least. Right, so just by looking at that graph, we get something along these lines, right? So that's all it means when it says using the graph or estimating the limit graphically, is drawing that picture and then moving your pen along the line of the graph. So that's our problem session for this time. Thanks, folks, for submitting these. Remember that there'll be one of these each week. It can be from the readings for that week or from the homework for that is been going since the last problem session. Let me know if there are any issues, and I will see y'all later.